Okay, so today I want to focus largely on the example of the free particle. And in particular, we're going to compute the free particle propagator, and we're going to do it in two ways, essentially. The first is, I guess, what you would call a direct approach, in which we're going to compute the propagator from its definition, that is, starting at a particular state, evolving that state forward with the Hamiltonian, and then projecting it onto a final state. And then we're going to compare this direct approach with the path integral approach. And I hope to convince you at the end of this class that the path integral approach is hopelessly too elaborate for this simple example. However, even though it's a very elaborate computation that's much more difficult than the traditional straightforward approach that you would have learned in quantum mechanics, it is nevertheless quite important because the path integral approach doesn't get a hell of a lot more complicated to compute the propagator, whereas the standard methods get much more difficult to compute for different physical systems. So that's essentially the point. So we want to benchmark what we've learned in this abstract construction of the propagator against a really simple, straightforward example, just to show that we can do the calculation and make sure we're getting the right answer. And then we're going to go through and make some observations about the free particle propagator, which will lead us to essentially the method of saddle point or semi-classical approximations. Okay, if we have time at the end of this lecture. But so let's start off then at the beginning, and I'm going to go through this particular example in some detail. So make sure you understand how it all works. And future examples, one of which is a standard example which you'll be tackling by yourself, which is the propagator for the harmonic oscillator, work in pretty much the same way, just with the change of potential and some tricks, let's say, with computing the propagator. So the example I want to start off with today is that of the free particle. And the free particle is defined by, so we want to consider a free massless quantum particle. Sorry, we want to consider a free massive quantum particle just propagating in space-time. Okay, so there's no potential in which this particle is propagating. It has mass m, and it is because there's no potential, it's what we call a free particle. Right, and we're going to compute. So what we want to do is to compute the propagator or path integral or path integral for, or amplitude for the Hamiltonian h equal to p squared over 2m. Again, I'm not particularly concerned with units and h bars and things that are floating around. We can always reinsert them at a later stage using dimensional analysis. So we're going to approach this problem in two ways. The first of which is so the first method is to use the definition of the propagator. So we want to evaluate the propagator directly. Now we know that this object, the propagator or amplitude, if you want, k of x prime capital T, x0 is what we get if we start off from a state at time t equals 0. We start off from a state x. We propagate the state forward in time with the Hamiltonian by acting on it with this e to the minus I h t, and then projecting that onto the final state x prime. Okay, so this is what we want. This is the object we want to compute. But we know already what the Hamiltonian is. So let's insert this Hamiltonian and then go through the standard procedure for what to do once you stick that in. So this is equal to x prime times the exponential of minus I t p squared over 2m. Okay, which is equal to x prime exponential of this minus I t capital P squared, this being the momentum operator, over 2m. Now, the momentum operator acts on momentum eigenstates, and so we should insert some momentum eigenstates into this by resolving the unitary. So we insert into here, we'll insert the identity operator, and then we'll resolve the identity operator by expanding in a basis of momentum eigenstates. So that I will write that identity as the integral over momenta of momentum eigenstate P in outer product P, and then here's my original state x prime. So this comes from the identity operator. Then the momentum operator acts on these eigenstates. Now, what I do, because I have an exponential operator, is Taylor expand the exponential, and then I have order by order terms in p squared and higher order terms. And I act successively at each order with this. And you can see that every time the momentum operator P, every time this momentum operator P here, this guy, acts on the momentum eigenstates, it pulls down a factor, or it gives me a factor of little p. And for each term in the polynomial expansion of the exponential here, I will get a corresponding term that is in the momentum eigenvalue and not in the operator. But the resulting term can then, the resulting thing can then be resummed, the resulting series can be resummed into another exponential. With the upshot being that once I've Taylor expanded, acted term by term, resummed the series, I get the integral over momenta of e to the minus I t little p squared over 2m. And what's left is x prime inner product p multiplying p inner product x. But as we saw, each of these inner products here is basically just a plane wave expansion. And so that's just a complex exponential, which is then the integral over momenta with this normalization, e to the minus I t p squared over 2m times e to the I p x prime minus x. Okay, and of course, I have two exponentials now, one of which is linear in p, and the other one is quadratic in p, which tells me that I can write this thing by completing the square as a Gaussian, a shifted Gaussian, and then it's just a matter of doing a shifted Gaussian integral. So this I'm going to leave for you to do that Gaussian integral, but it will come out to be m over 2 pi it. All right, I'll back in a second. Sorry about that. Somebody at the door. Square root e to the I m x prime minus x squared over 2t. So that's it, actually. That's the answer for the propagator for a free particle Hamiltonian. Any questions?
No.
Nitin, you have a question?
No questions.
Okay. So just for completeness here, I'm going to make a note and ask you to quick calculation. Do the Gaussian integral. Okay. All right, so that was the easy one. That was the easy calculation. We basically just do the expansion as we would expect. And you do the expansion as you would expect, act on it with the operators by inserting a resolution of the unity in momentum eigenbasis, and follow that up with carrying out a Gaussian integral. There's an in-between completing of the square story that you need to do, but by now that should be quite straightforward for you to do. Let's now progress on to the path integral computation for this. So in the path integral computation, remember, we have a definition of what the path integral should look like. This k of x prime t x naught that I want to compute is the formal path integral having carried out. Okay, so this Hamiltonian is clearly in a quadratic form, which means that I can, in my phase space path integral, integrate out over the momentum variables, which leaves me with an integral over configuration space, in which case this integral, the path integral, is the exponential of I times the action functional, which is a functional of x of t. Okay, so this is what we want to calculate. And I said the last time, and it's worth it's worth repeating, that this thing here is really just a shorthand for the following limit. The limit is that n goes to infinity, epsilon goes to 0, in such a way that n times epsilon is fixed to be the interval from 0 to t. So it has length t. This is really the limit that we're going to want to take here. And in what follows, I'm just going to write the limit, and we understand that this is what I mean. N goes to infinity, epsilon goes to 0, n times epsilon is the fixed time scale, the fixed time length that we're looking at, which is capital T. And sitting in here is this factor that we found was m over 2 pi I epsilon raised to the n over 2. And Nitin questioned the last time how we take this. I think it was Nitin that questioned the last time how we take this limit, because epsilon is going to 0, n is going to infinity. How do we take this limit in this prefactor? And I'll show you with the free particle precisely how this limit is taken now. Then I had some integrals to do. In fact, I had n minus 1 integrals to carry out. The n minus 1 integrals are taken over the intermediate states, x1 through to xn, with x0 being x and xn being x prime. And then the discretized version of my action looks like the exponential of I times m epsilon over 2 times the sum over I equals 0 to n minus 1 x xi dot squared. So that's just a half mv squared, a half times the a half m times the velocity squared, and the epsilon here comes from discretizing the integral. So this epsilon here comes from discretizing the integral, and the sum comes from discretizing the integral. Okay, any questions? Right, so this is the limit, with my caveat about what I'm calling the limit here. M over 2 pi I epsilon. I'm going to hold this thing all the way through to the n over 2, sorry. Integral over x variables. Now I'm going to expand the sum out by expanding what I mean by x dot in this story, right? X dot was an abuse of notation, meaning d by dt, but in this case, we've already discretized the integral, so let's discretize what I mean by this derivative as well. So that's exponential of I m epsilon over 2 sum over I equals 0 through to n minus 1 of x I plus 1 minus xi over epsilon. And this is what I'm squaring. So this is what I meant by x dot in my definition previously. Okay. So it will be useful for us to expand this thing out completely, because I want to show you a trick that we're going to use to evaluate what is effectively a formidable looking integral. But the first thing is to identify what it is we're actually working with. So this is the limit. Again, as n goes to infinity, epsilon goes to 0, n times infinity, n times epsilon being a fixed number, 2 pi I epsilon m n over 2. Now, the integrals that I have to work with are the following: n minus 1 through x1. And I take the exponential of I m over 2 epsilon times x n minus x n minus 1 squared plus x n minus 1 minus x n minus 2 squared. And this goes all the way through to x1 minus x naught squared, like that. Okay, where, just by way of reminder, this is what we were calling x prime, and this is what we were calling x. So that's the integral that we have to do. And at this point, I've got some good news and bad news. And the good news is all the integrals that we have to do are Gaussian. They all go like something e to the minus something squared. Okay. The bad news is I have to do n minus 1 of these Gaussian integrals, but they're all coupled. So I can only do the Gaussian integral in x minus in x2 if I know what the answer for x1 is. I can only do the one in x3 if I know what the answer in x2 is, etc., etc. Right? So I actually can't just say I have, which is what I was hoping I would be able to do, that I have just n minus 1 Gaussian integrals. They're all decoupled, so I only have to do one of them, and I can just stare at the answer. Okay, so that's the problem, but it's not an insurmountable problem. In fact, as long as we're systematic about how we approach it, it's actually not that formidable an integral. Okay. And to make our lives a little bit easier, what we need to do is make a change of variables. So let's make a change of variables. From the xi to, let's say, qi, where I'm going to define, the 3 lines here means I'm making a definition, where I'm going to define qi to be the square root of m over 2 epsilon times xi. So from here, I get that each of the xi integration measure variables, dxi, is the square root of 2 epsilon over m times dqi. Okay. And in terms of which, the integral that we are looking for, k, can be written as the limit as n goes to infinity, blah, 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 of m over 2 pi I epsilon to the n over 2. That's the prefactor that we're carrying around, times, coming from the integration from changing variables, 2 epsilon over m to the n minus 1 over 2, times an integral over q variables, dqn minus 1 through dq1 times the exponential of I times qn minus qn minus 1 squared plus all the way through to q1 minus q naught squared, etc. So I haven't really made my life too much simpler in this story. But in changing variables, I'm going to take care of a whole bunch of prefactors of m's and pi's and i's and epsilons that I don't want to lug around for much longer. So you can show that these two prefactor terms here, much cancellation happens, and we will come back to it in a little bit, but there's n over 2 factors of m in the first term, and there's n over 2 minus a half factors in the second term. The n over 2's cancel out. Similarly, there's an epsilon in the denominator, there's an epsilon in the numerator. There's n over 2 factors in the one, there's n minus 1 over 2 factors, there's n minus 1 over 2 factors in the other one. And you can see where this is starting to shape up to is a square root that looks similar to what we got in the direct case. But we still have to actually do the integral. So what I'm going to do is systematically approach the integral, working from inside to go out, right? So we're going to start with the Q1 integral, then we're going to go to Q2 integral, etc. And we're going to see that we're going to be able to spot a pattern pretty quickly. And so we don't actually have to do all the integrals. We're going to write down the first couple of integrals, see if we can spot a pattern, and then more or less write down a general formula, which we're going to stick into it. So to do the integrals, I'm going to define the following. Let's call it the innermost integral I1, and I1 by my definition is just going to be the integral from minus infinity to infinity of the exponential of, now I'm gathering all the terms in the exponential that have an I1 factor in it. And in fact, there are two of them. They will look like, sorry, they will look like I times Q2 minus Q1 squared plus Q1 minus Q0 squared. And then we've got to close brackets and close braces. Okay. So this is the integral we have to do. Again, this is just a Gaussian integral. I'm now thinking of Q2 and Q0 as, I'm thinking of Q2 and Q0 here as fixed variables. Q2 is, of course, Q1 is, of course, fixed, and Q2 with respect to Q1 integral is fixed. Okay, so this is just a shifted Gaussian, which you can show by completing the square again and carrying out the Gaussian integral. And what you will find is that I1 is simply I pi by 2 to the half times e to the minus Q2 minus Q0 squared over 2i. Okay, so that's great. That's a nice result, but it really is just a Gaussian. The point here is that we use this Gaussian in the Q2 integral, because if I feed this into the integral over Q2, that integral looks like this. So I'm going to call that I2, and I2 is the integral just like the one I had, except I'm gathering all of the I2 pieces, and the I2 pieces will have one term that goes like Q3 minus Q2 squared, and another term that goes like Q2 minus Q naught squared that comes from I1. So if I feed this back into the I2 integral, this looks like I pi over 2 to the half. That factor comes from having done the I1 integral. Integral from minus infinity to infinity of dq2 e to the I q3 minus q naught squared e to the I q2 minus q naught squared over 2. Again, this is nothing but a Gaussian in Q2. And you can do that Gaussian integral, and you will find that once you group terms appropriately, this thing can be written as I pi squared over 3 to the half times e to the minus Q3 minus Q naught squared over 3i. And I'm choosing to write it in this particular way because it will allow us to find a pattern. So the I1 integral, so let's just highlight this guy as well.
Wait, sorry, Prof. For the I2, shouldn't it be Q3 minus Q2, not Q3 minus Q0?
No, I've already substituted. You're quite right. It's Q3 minus Q2, but I've already substituted from the I1 integral.
Oh, okay.
So it's Q3 minus Q2, and then Q2 minus Q1.
Okay.
You with me?
Yes.
So I need to substitute for the I1 integral back into the I2 integral. So I've already done that. Sorry, I've skipped out a step there.
Okay.
Right? But I'd like you to look at the two highlighted exponentials. The one is the result of the I1 integral, and the I1 integral is an I pi over 2 to the half e to the minus Q2 minus Q naught squared over 2i. And the I2 integral is an I pi squared over 3 to the half e to the minus Q3 minus Q naught squared over 3i. So you can see that if you don't believe me, you're welcome to continue and do another integral. But there's a pattern here, and if I follow this pattern, we'll find that the nth integral, the n minus first integral, in minus 1, will come out to be I pi to the n minus 1 over 2 over n to the half, square root of n, times the exponential of minus qn minus q naught. These are the only two q variables that we're not integrating over, and hence they must remain, over I times n. Or in terms of our original variables, the x's and not the q's, this would be I pi to the n minus 1 over 2 over n to the half times the exponential of minus m times x prime minus x squared over 2 epsilon n times I. And now we're at the position where we can take the limit, and we want to take the limit of so k is the limit as n goes to infinity, epsilon goes to 0, and epsilon is fixed at capital T of the square root of 2 pi I n epsilon m e to the minus m x prime minus x squared over 2 epsilon n times I, which is nothing but the square root of m over 2 pi I times t e to the I m x prime minus x squared over 2t, which is precisely what we were hoping for, because that's what we got in the direct case. Everybody happy with this?
Yes.
Great. And you can see what happened with that factor of epsilon and n that we had. You had just enough cancellations, and the combination of n times epsilon to give you the fixed time t to allow you to take that limit. Okay?
Yeah.
Great. So at this point, there are a couple of points that I need to make. Let's just erase this. Okay. There are a couple of points that we need to make. The first of which is the fact that the argument of the exponential is a rather clean form for us to deduce how this particle is going to be moving. Remember, we're considering a free particle moving in flat space. And so you would expect that a free particle moving in flat space would move in a? Anyone?
Sorry, I didn't get you.
How would you expect a free particle moving in flat space to move? What is GOD6? Just guess. Take a guess.
It will continue moving however it is moving in a straight line.
Great. Straight line is the word I'm looking for. Okay. So let's show how this is the case. So let's make some notes here. These are general notes about the problem. So it's, I'm done with my example. So I'm just going to write down some general statements. And the first one, okay, so let's note. Point one is that I can write the argument of the exponential in the following form. The argument can be written as t times a half m times x prime minus x over capital T squared. So if I have this particle that starts off in the state x, ends up in the state x prime after some time t, and there's no potential. So there's no forces acting on this particle. So I would expect it to be moving at constant velocity, and that velocity would be x prime minus x over capital T. And I would expect that its energy would be a half mv squared, in other words, a half m x prime minus x squared, x prime minus x over T all squared. And so I would expect that its action, its classical action, remember we did a quantum computation here, but I would expect that its classical action is nothing but that constant velocity integrated out, sorry, that constant momentum, that constant kinetic energy integrated out over time, which would just give me a factor of t. In other words, this is the classical action for a particle moving along a straight line connecting x and x prime at constant velocity. Let's phrase this like this: for a free particle moving in a straight line, okay. The second point is that, again, we're doing a quantum computation. And so with any quantum computation, you would expect to have factors of h bar floating around, because h bar, recall, is a measure of how quantum the computation is. And in the limit where h bar goes to 0, you'd expect to have, to recover your classical computation. But there aren't any factors of h bar floating around here, but that's only because we've dropped factors of h bar for convenience, and you can restore these factors of h bar by dimensional analysis. And I'm going to leave that as an exercise for you to restore factors of h bar and write down the full expression for the amplitude by restoring factors of h bar. So the way you would do that is to first keep in mind that h bar has units of energy times time. And so it would be reinserted in the weighting factor for the path integral. So it should go like e to the I s over h bar. Then work out what the correct dimensions of the propagator are. And once you got that, you can figure out how to insert factors of h bar into the propagator from dimensional analysis. It's a useful exercise to carry out because it'll give you an idea of how to think about the propagator for more complicated problems. Any questions? Okay, so I don't want to start the discussion on semi-classical methods right now. I will do it on Wednesday, in which case I want to illustrate the semi-classical or saddle point approximation just by trying to work out a straightforward one-dimensional integral and showing you how to get some intuition for what's going on here. And then we'll bring it back to the path integral. Okay? Any other questions? Okay, so if not, I'm going to stop the recording. Thank you very much, and I will see you guys on Wednesday.
Thank you.